Hello, everyone. I'm Paul Boutot. I'm from Toronto Metropolitan University, and I'll be presenting IoTMoF, a requirements-driven modeling framework for IoT systems. So when developing IoT systems, they're often very heterogeneous in nature. This is because of the many different design decisions that can be made, as well as the different elements that are included in making such systems. Because of this, there are often many intricate interactions, and the failure to capture these interactions increases the risk of developing systems with missing functionality and incorrect or incomplete implementations. Thus, there is a need for a requirements-driven modeling framework, as specifications can be used to generate detailed design models and synthesize code. Thus, we propose IoTMoF. I'll be going into more depth in a little bit about this, but basically IoTMoF provides platform-independent modeling, platform-specific modeling, and code generation. But before I get into that, I'll talk about some background information, starting with the Internet of Things, which you may already know, which is a heterogeneous set of interconnected things, middleware, and software. The main facets of the IoT being the software, the environment, the hardware, and the network. The software is the core entity behind all smart systems and is what controls the interaction between the system and various aspects of the IoT system. The environment is what is comprised of human users and physical entities and smart devices. The hardware is what facilitates interactions, and the network is what enables communication between the various things within the system. Moving on, we have use cases. Use cases are a way of modeling interactions in systems. On the left is abstract syntax of use case diagram. Specifically, you can see how here there's an actor. The actor will have use cases with the system, the use cases being goals, and use cases can include or extend other use cases. The concrete syntax will basically describe how these elements will look. So for example, an actor would be represented through a stick figure and a use case would be represented through ellipsis with the name of the goal. On the right, you can see an example of that. Here, there's a waiter, for example. The waiter is represented through a stick figure and is named waiter, and this waiter has goals with the system, the goal being to order food. Textual use cases are descriptions of UML use cases. They basically describe how use cases can be achieved through steps. On the left is another abstract syntax, basically describing the core ideas behind the language. You can see how there are main success scenarios and extensions and how there are steps. On the right is an actual example of a textual use case. Here you can see how there are steps. The main success scenario basically describes the main flow of interactions to achieve the use case, and extensions describe how, like, alternative situations. Exceptional use cases are an extension of textual use cases. Basically, they introduce the notion of exceptions and handlers in textual use cases, exceptions being exceptional situations that interrupt the normal flow of interaction. These exceptional situations can be handled through a special type of use case called a handler use case. This use case basically defines interactions that are necessary to handle the exception. Moving on, we have state charts. State charts are used to describe the behavior of event-driven systems. On the left is a simple example of a state chart. There's of a light switch. The light switch can be in two states, on or off, and it can switch between the two states through an event called toggle. On the right, there's a more complex example. This is basically describing a light switch with light sensing. Will switch between the two different states based on some light threshold. If the light intensity of the room, for example, is too low, it will turn the light on. If it's too bright, it will turn the light off. And finally, we have the IoT ARM. The IoT ARM stands for the IoT Architectural Reference Model. Basically, it is a step towards a standardization of a reference model for the IoT. It provides a domain model schema with common IoT elements, and this domain model includes two types of users, human users and digital artifacts. Users can interact with physical entities, and physical entities can be anything found within an environment, such as plants or animals or technology. Devices are a type of physical entity. There are three types of devices: actuators, tags, and sensors. Actuators act on physical entities, tags allow physical entities to be identified, and sensors monitor physical entities. Here is a complete picture of this domain model. There's some other things I did not introduce, specifically services and resources. Services can be, users can invoke or subscribe to services, and services can expose resources. And finally, we are moving on to our approach, the IoTMoF. IoTMoF is a requirements-driven modeling framework that covers model-driven requirements, development, design, and code generation for IoT platforms. IoTMoF builds on Recam IoT, which is our previous work, by providing platform-specific modeling and code generation. Specifically, Recam IoT provided textual use case modeling for IoT systems, as well as the generation for IoT use case diagrams, summary tables, and IoT domain models. IoTMoF provides this as well, along with IoT information model editing, configuration model mapping, state chart mapping, and code generation. This is a requirements-driven modeling framework because we use textual use cases as the source model for all of the things that we generate throughout the framework or the process. Moving on, this is the complete picture of our approach. Basically, we start with a textual use case model called USIM for IoT. Using USIM for IoT, we generate an IoT use case diagram as well as an IoT domain model. From the IoT domain model, we create an IoT information model. And from using the USIM for IoT model and the IoT information model, we can create a state chart and configuration model. From there, we create code, and then that code is eventually deployed onto a smart device. We tested this on a simple smart lights IoT system. The goal of the system was to read an external light intensity. If the external light intensity was dark, it will turn an LED on. If it was bright, it will turn an LED off. It would also send data to a server. Moving on, we will talk about the various aspects of IoTMoF, starting with platform-independent modeling. Here, we'll talk about textual use case modeling, as well as the generation of use case diagrams, summary tables, and IoT domain models. USIM for IoT is how we is a language that we created. It's a textual use case modeling language. The name USIM for IoT stands for a use case modeling for the Internet of Things, and it extends traditional use case models with IoT-specific elements. This was published in SAM 2021. And basically, USIM for IoT, this is the abstract syntax. I'm not going to go into too much depth here per se, but basically, we extended this from textual use cases, exceptional use cases, and the IoT ARM domain model. Specifically, we include the notion of like descriptions of use cases through steps. We also include the notion of exceptions and handlers, and the notion found from the IoT ARM domain model, specifically humans, devices, or physical entities, or software. You can define actors in USIM for IoT. Here, for example, you can define actors up here in the use case in the USIM for IoT file model. There are 4 types of actors: human, software, devices, and physical entities. And there are also 3 types of devices: actuators, sensors, and tags. You can also define and raise exceptions in USIM for IoT. There are 4 types of exceptions: hardware, software, network, and environment. And of course, you can define handlers. Handlers are a special type of use case that are specifically created to handle exceptions. Here, you can see how this handler is just a use case prefixed with handler tag, and there's another tag specifically mentioning exceptions that will handle. Moving on, you can also define steps to describe how a use case can be achieved. There are several different types of steps in USIM for IoT. There are control flow steps and condition steps. There are invocation steps, which are used to invoke other use cases, and interaction steps, which define an interaction between the system and an actor. Here you can see how there's an interaction between the system and the customer actor here. There's also internal steps. Internal steps define internal processing within the system, and there's exception steps, which are used to raise exceptions. We can use the USIM4IoT file to generate an IoT use case diagram. The IoT use case diagram will contain IoT concepts, specifically the actors are typed. There are handlers and exceptions, and the exceptions are also typed, and all use cases found from the USIM4IoT model are also here. We can also generate an IoT domain model. The domain model is used basically to describe the domain of the IoT system being developed. The various entities found from the USIM4IoT model are mapped onto this domain model, and the relationships are also mapped using keywords. So for example, if there's an actor, and there is the keyword axon followed after that actor, followed by an optional article and a physical entity, then that will define an axon relationship. There are other types of relationships too that are used in the mapping process. Here you can see an example of that. This LED here acts on the physical surroundings by providing light. And there's a sensor called LDR, which monitors the physical surroundings. Moving on, we have platform-specific modeling. That includes IoT information modeling, state chart generation, and configuration model generation. We can create an information model from the domain model. This information model will basically include design level decisions that are not found from the domain model. Here you can see how these devices from the domain model are all attached to a physical entity called SmartLed device. There's also a network resource. These are design level decisions that won't be made at the requirements level or platform independent level. There's other things you can't really see in this model. For example, you can create code annotations and pin annotations. These are other design level decisions that we'll talk about in a bit, but are necessary to define like how this can be used in the system. This is the state chart. This state chart, a textual state chart specifically. This state chart is generated from the USIM4IoT model as well as the information model. Basically, you can see here how there are states and composite states. Composite states include states inside of them, and you can also transition from one state to another. The generation process includes like multiple roles using multiple aspects of the USIM4IoT model and the information model. Specifically, we will use summary level use cases featuring a human or software actor or a device actor. We'll also look at modes and exceptions and handlers from the USIM4IoT model and the different devices found from the information model. So for example, when it comes to summary level use cases, we'll generate a composite state, and this composite state will basically include all the state, will map all the steps found from the summary level use case onto this composite state. Speaking of, if any steps are invocation steps, those steps will be mapped as composite states as well. And this is a recursive operation. If the invoked use case has steps inside of it, those steps will be mapped. And if any of those steps are invocation steps, those steps will also be mapped as composite steps. Internal steps or interaction steps or any other kind of steps will be mapped as states. And modes found from the USIM4IoT model will be mapped as separate states. So for example, if there are two modes from the USIM4IoT model, there will be two modes that those two modes will be mapped as states in the state chart. Moving on, we have exceptions. For each exception, there are two events that are raised. Specifically, there is a raised event, basically describing when the exception gets raised, and there's a handled event, basically describing where the exception gets handled. And finally, we have handler. The handler will be mapped as into multiple aspects in the final state chart. There are two things. So for each handler, there's an idle state and a composite state. The idle state is when the handler is not doing anything, and the composite state will basically describe when that basically describe the behavior of this original use case. When an exception, specifically an exception that this handler handles, that idle state will transition to the composite state, and then it will start invoking that behavior. Moving on, we have the configuration model. The configuration model is used to describe like the device's behavior of this and how it can interact with the different devices in the system. In our case, we use an ESP32 when creating a smart light system. The ESP32 has many pins, as you can see on the sides, and these pins are what it uses to interact with different devices like LEDs. Here is an example of what the configuration model looks like. On the left, you can see components like LEDs and the pins that are connected to the devices connected to. And on the right, you can see the functions and how you can interact with those devices and how you can get those devices to do things. So for example, an LED can turn on or off by running these functions. The rules for generating this is simple. Basically, for each device and its set of pin annotations, it'll create a component with the list of pins that it uses, and for each device and code annotations, it'll create functions describing how that device can be used. Moving on, we have code generation. Code generation is the process of generating code from the state chart and the configuration model. The state chart code is used to describe the behavior of the system, and the configuration code is used to describe the platform specific decisions, like how do you read in sensor values or how do you turn on an LED. Here is an example of the configuration model being mapped onto code. You can see how the pins are mapped as constants and are set up in the setup function. And you can also see how these functions are also mapped below. For the state chart on the left, you see a bit of a snippet of the state chart. And on the right, you also see a snippet. Basically, again, it will describe like how the behavior of the system. These are some of the functions that have been generated from the state chart. Anyway, in wrapping things up, what we ended up creating was a requirements-driven IoT modeling framework called IoTMoF. This was built on top of Recom IoT. IoTMoF introduces IoT information model editing, generation of configuration models, state charts, and Arduino code. Here, basically, again, I'll go over the process. We start with the USIM for IoT model. Using the USIM for IoT model, we generate an IoT use case diagram and an IoT domain model. From there, we use the IoT domain model to create an information model, and we use the USIM for IoT model and information model to generate the textual state chart and the configuration model. Finally, we generate code, which is then deployed onto an IoT device. Exceptions and handlers are basically mapped from the USIM for IoT model all the way to code. And this ensures that the final implementation is reliable and complete. In terms of work in progress, we're trying to ensure that models are kept in sync. Right now, whenever changes are made to the USIM for IoT file or model, those changes are propagated up to the other models. However, in terms of future work, we would like to do the opposite, where if changes were made to the information model, it will also update the USIM for IoT model. We also aim to provide validations with more complex systems. We have tested the platform-independent modeling and platform-specific models or modeling on previous systems, case studies like the smart fire detection system. But we would like to also test the code generation on more complex systems in the future. And that is then my presentation. Are there any questions?
Thank you.